Hello everyone. Now in this video I'm going to show you how to simulate this flooding attack on IoT nodes running RPL protocol. This flooding attack is one of the attacks that is being performed on this RPL routing protocol. And a flooding attack is an attack that consists of generating a large amount of traffic in the network with the sole purpose of making the nodes and links unavailable. And in worst case, such attacks can exhaust the resources of all the network nodes. And when using a solicitation message to perform the flooding, the attack is called a hello flood attack. So to perform this flooding attack in RPL networks, an attacker can broadcast, can either make a broadcast this packet, and we know that this is a DODAC information solicitation, and it is a packet that is used by a new node that wants to join an existing DODAC. So if you want to join an existing DODAC, destination-oriented directed acyclic graph, it is going to transmit this packet, making an inquiry that it was making a request that it wants to join the DODAC. So now a malicious attacker will now abuse this mechanism and then broadcast this message to the neighboring nodes, or it can send a unicast this message to each node, which must reply with a DO. Now DO stands for DODAC information object, which is another control packet used in RPL administration. So when a new node sent this packet, now the existing node in the existing DODAC will reply with a DO, DODAC information object. So to implement this attack, we perform some changes to the normal source code of the RPL implementation in the Contiki operating system. And one of those files to be modified is located in this particular directory, contiki/co/net/RPL. Now there is a file called RPL-private.h. Now this particular file contains private declaration for the Contiki RPL implementation, such as the default values for the ICMP, that is Internet Control Message Protocol, control messages, and the timers associated with them, the mode of operation, and the DAG routing tables. And then also there's another file called the RPL timers.c, which is the RPL timer management implementation in the Contiki operating system. So what changes do we perform to the RPL-private.h? We know that RPL-private.h includes several constants related to the disk operation. So the flooding attack is implemented by decreasing the value of the disk message interval and the disk start delay to force the malicious mode to send this message as quickly as possible. So as you can see in this particular file, RPL-private.h, in line 9, 185 to 193, particularly in line number 190, that is where we make our changes. We can see that particular macro, we set the value of that particular macro to 0. Hash define RPL disk interval, we change it to 0. The value, the original value was 60. We now change it to 0. And then also the other macro, RPL disk start delay, we set the value to 0. The original value was 5. So these are the changes that we need to perform in the RPL-private.h file. Now the other changes, we perform changes in the RPL timers.c, which is another file. Now within this file, we locate this particular line of code, static void, where it starts static void, particularly in line number 11. This particular making this particular addition in line number 12. A loop is added in the periodic timer function to send a total of 20 disk messages without any conditions. So I will provide these files with all these modifications, so that all you have to do is to create a new Contiki instance, name it this flooding attack, and then replace those files, the RPL-private.h and the RPL timers.c, with the malicious modified files that I'm going to provide to you, and then from there you'll be able to generate a malicious node from that particular modified Contiki instance. So now what we are going to do, we are going to go to the Contiki operating system and then perform this simulation of this particular plugin attack. So let's go to Contiki operating system. So this is my Contiki 3.0 operating system. Now I'm going to go and load Kuja. So I'll just launch my terminal, and then I'm going to launch the Kuja simulator. So I'm going to navigate to CD Contiki 3.0. I'm going to go under Tools, Kuja, and then let me clear the screen. And then I'm going to run this command sudo and run, and I'm going to enter my password user. Alright, so this is my Kuja simulator. So I'm going to create a new simulation. So the first thing I'm going to do, I'm going to create a normal simulation, and then observe the simulation and the behavior of the nodes in that particular simulation. Normal nodes, there's not any malicious node. And then next we add a malicious node, and then notice the changes in the observable behavior of the modes under this particular disk loading attack. Particularly the power consumption. We're going to go and see the power consumption of the nodes before a disk loading attack and after a disk loading attack. So what I'm going to do now, I'm going to go under File, New Simulation. I'm going to call it this attack, but I'm going to start with this normal simulation, but I'll just call it this, or let me call it just this, so that not to discriminate against the normal simulation and the malicious simulations. So let me just call it this, and then we're going to create. So this is my simulation environment. Now I'm going to add the mode. Mode is just like the adding the IoT devices to the network. So mode, add mode, create a mode type. I'm going to select Z1, that is Zonesia device, or Sky, T-mode Sky. So any of these are the most frequently used modes for performing simulation with this particular Kuja. So I'm going to select, I'm going to go for Z mode this time around. So I go to Z mode, then I'm going to browse create a simple refill network. So I'm going to go under Contiki 3.0. I'm going to go under examples. I'm going to go IP version 6, refill collect. And then I'm going to go, and first of all, I'm going to set up the root node. That is the root node, the border router. So UDP sync sync.c. I'm going to open it. I'm going to clean to make sure that, so I want to make the compilation from the start. So next I'm going to compile. So I'm compiled, and I'm going to create a mode that is using this part, that is that this particular firmware UDP sync, that is the software responsible for running a border router and a refill network, is going to be uploaded to an emulation of this particular mode. Mode is just is similar to a replica of an IoT device. So when we say mode, a replica of an IoT device. So this will serve like our root node in the refill topology. So I'm going to create. I just want one. Add mode, just one. So under view here, I'm going to enable some options like the mode type, so as to differentiate between the different modes, and also radio traffic. Okay, radio traffic is already enabled. So let me leave it as it is. Now I have created the root node, the sync. Now I want to add the normal routers on the network, that is normal devices. We know that a refill network, all nodes, many nodes can serve as a routers. Though we can have non-router devices like leaf node. So I want to add the normal nodes that are not root nodes to the network now. So I'll just go under mode again. I'm going to say add mode, and then create new mode type. I will still go for my Z1 mode, and then I'm going to browse, and I'm going to select UDP sender.c. So I'm going to select it, open. I'm going to clean, and then because I'm cleaning because I want to start the compilation process from the scratch. So compile. Okay, perfect. So I'm going to create now. So I want to add now 11 modes. Add modes, 11 modes. All right, so here we are. I have modes. I've added modes to the network. Let me maximize it. So we have our root node here, and the root node. Okay, so let me bring the root node to the center. Let me bring it here. So all the modes now, you know the default traffic in the Ripple network is the offward traffic. That is, okay, sorry. I want to shift the whole modes. I want to shift the whole of the modes. I want to bring them to the center here. We know that in a Ripple network topology, the direction of the traffic is upward direction. That is, all the modes are trying to send their data to the sink, to the root node. Here in this, all the modes aside from the number one, which is the sink, are trying to send their data to the root node, and any node that is not in the transmission range of the root node, like this node 11, will have to make use of another mode to forward, that will forward its traffic to the root node. So in this instance, we call that a parent node. So now 9 can serve as a parent node to node 11, because now 11 doesn't have any alternatives than to select 9 as it is parent node, because it is the only node within its transmission range. If we click on the node 11, we can see with this area within this green, there is only one mode that is within the transmission range of this mode 11. So this mode 11 has no any available option that to select 9 as it is parent to forward its traffic to the sink. So that is how the Ripple network works. But as for 9, it is also not within the transmission range of the root node, so it can select either 6 or 2 depending on the rank. Depending on their rank, it will select the one that has the best rank to serve as its parent to forward its rank to the root node. So that is how you can read more about Ripple. I've also created a video on how the Ripple routing protocol works. You can watch the video and see how the Ripple routing topology protocol works. So next, we want to collect the data, the simulation behavior of this particular simulation. For that, we make use of another tool called collect view. So I'm going to click on this root node. I'm going to right click on it, more tools for Sky1. I'm going to select collect view. So this collect view will be the one to collect the power consumption, especially it gathers a lot of data pertaining to the nodes in the topology. But we are more particularly interested in the power consumption of the node under, before, and after malicious attack. So we want to, and then all that data will be available via the root node. Since they are sending their traffic to the root node, we can make use of the root node to know about the power consumption behavior of this particular mode that are in this particular IoT network. So I'm going to say start collect. Then I'll say same command to nodes. So I'm going to minimize it now. So now I can go and start my simulation. Let me minimize it, and then I'll just come and click on here, and then it will start the simulation. So let's leave the simulation for say 6 to 7 minutes in this particular time. Within this time here, once it reaches 7, I'm going to force the simulation, and then we are going to see the behavior, or let's see 5 is okay. So we're going to see the behavior of the modes under without malicious attacker in the routing topology, and then we are going to add a malicious mode and then see the behavior, the power consumption of the mode before and after a malicious disk loading attack. So I'm going to pause the simulation now. Once it reaches 5 minutes, then I'm going to come back and then see the simulation behavior of the modes. Thank you. All right, so now I'm going to pause the simulation. Let's pause the simulation and then go to our collect view and then see the power consumption of the mode. So go under power. So we can see the power consumption of the mode. You can see the highest power consumption is 0.75. The unit is in megawatts. So we can see the highest power consumption is performed by mode 10, and the highest is 0.75. Let's see it. This is mode 10. With mode 10, this is mode 10. It has the highest power consumption of 0.75. So let's note the power consumption of the mode so that when we come to perform our disk loading attack, we can see the power consumption of the mode. We can compare and contrast before and after the attack. So this is the power consumption. The highest power consumption is 0.75. So let me make note of it here under notes here. So highest power consumption is 0.75 megawatt. Highest power consumption is 0.75 is 0.75 megawatts. Okay, so this is the power conversion. That is before attack. Before attack. Now next, after the attack, let's see what we are going to get. So after this loading attack, after this loading attack, let's see how the highest power consumption is going to be. So now what I'm going to do, I'm going to reload the simulation. I'm going to come here, reload the simulation, and I'm going to add a new mode, the malicious mode, the malicious disk loading attack mode, and then notice the changes in the power consumption of the modes. So what I'm going to do, I'll just come over here under my modes. I'm going to delete one of the modes. I'm going to delete, let me delete this mode 3, or let me delete the one with the highest ID. So let me delete mode 12, and then I'll come here under modes. I'll add mode, create new mode type, still go for Z1 mode, then browse. Then I'm going to go to my malicious Kentucky instance that I created, and then introduce my the malicious disk loading attacking mode. So disk loading, this is it. I'm still going under examples, IPv6, refill collect, and then I'm going to go UDP sender.c. UDP sender.c. I'm going to select it. I'm going to open it, and I'm going to clean because I want to start my compilation process from the scratch. Compile, and then it's going to compile a malicious RPL disk loading attacking mode for me. All right, so now I'm going to create it. So create. So just one mode, add mode. So let me zoom out. Zoom out. All right, let me zoom out again. So if I click on this mode 12, we can see that there are many modes within its transmission range, including the root node. So it's going to have a large effect on this particular network, the disk loading attack. So next, I'm going to go to the power collect. I'm going to say start collect, and I'm going to send command to node. And then now I'm going to start my simulation. I'm going to start. So also we are going to allow the simulation to run for some time, and then we're going to come back to observe the behavior of the simulation after the power, especially the power consumption of the mode after the disk loading attack. So I'm we'll force it. I'll force the video, and then we'll come back and observe the behavior of the mode. Alright, so I'm going to stop the simulation now. It has reached for 10 minutes. So I'm going to stop it, and then you're going to go to the collect view and then see what see what we'll be able to observe from the simulation behavior of the nodes under this loading attack. So under power here, we can see that the power consumption has reached up to 22.5. 22.5, and the lowest, which one is the lowest? The lowest power consumption is around something up to not up to 2.5, but the highest power consumption is 22.5. So it is more than what we have under the when we are not having attack on the node. Let me see it whether I can still get it. Let me see it on the note. On the note, I make a note of that. So you can see that the highest power consumption was 0.7 megawatts, but now we are having the power consumption reaching up to 22.5 megawatts. So 22.5 megawatts. So we can see it. So we can see that it has a negative effect on the power consumption of the mode under this loading attack. So our malicious mode was mode 12. It was the one with the highest power consumption. And which other mode has the highest power consumption? These are the modes. Mode 3. Let me bring it here so that we can be seeing the modes. We have mode 3, mode 3, mode 3, mode 3. Where is the mode 3? Mode 3, the third mode with the ID of 3. Where can I locate it? Okay, it is here. So we can those communicating with the malicious disk-loading attacker, with those within the neighborhood of this disk-loading attacker, are the one mostly affected with their power consumption. We have the other one with the highest power consumption. So we can see not mode 4. We can see this is mode 4. Mode 12 is the attacker, and then mode 8. Where is mode 8? We can see mode 8. Mode 7.0, mode 7. Look at it, and mode 5. So those ones within the transmission range, within the neighborhood of the malicious attacker, they are the one mostly affected by this disk-loading attack performed by this malicious mode. So we can imagine when we have this multiple disk-loading attackers on a particular network, the effect it is going to have on this IoT network. So this disk-loading attack is a very it is an attack that has a much negative effect on the IoT devices running this particular rifle protocol. So thank you for taking your time to watch this video, and please subscribe to my channel. And I am particularly working on this rifle routing protocol, so you can follow me on my ResearchGate profile. Look at it here. I'm here, Faisal Igarba. You can see, and I'm in the process of carrying out my research working on this particular ripple protocol. I can download my papers and go through them and see what I'm working on. So thank you for watching your time, and particularly please subscribe to my channel so that you can be able to see when I upload new videos on this Internet of Things, and particularly routing for low power and low C network. Thank you.